Hello everyone, welcome to our presentation on the Naptha Cracker Control project. This is Group 2, comprised of me, Devor Valdez Ariran, Chantal Albecker, and Andrew Chadwell. Our objectives for this project are implementing a control system that meets primary objectives, test the process control system, and finalize and implement dynamic controls on the Naptha Cracker system. Our objectives for the process control is maximize profit, maximize efficiency, and maximize safety. This is making sure that the excess O2 levels are kept above 9% at all times. For our process identification test, as an initial guess, a feedback controller was implemented to regulate the reactor temperature using the fuel flow valve. As we can see in the graph, a 10% step change was made in the input at 300 minutes. That's about 5 hours. The initial steady state was 118.5 degrees Fahrenheit, and the final steady state was 142 degrees Fahrenheit. This means a change in output of 23.5 degrees Fahrenheit. With this, we were able to find the gain of the process, which was found by dividing the output change by the input change, giving us 2.35 degrees Fahrenheit per percent output of the controller. Then, using the graph itself and the 6328 method, we were able to find the time constant and the delay of the process. With these three variables, we were able to make a transfer function for the process, as we can see in the image at the left side of the screen. Here we can see a table with the results for the three tuning methods for Ziegler-Nichols, Dowling 5% overshoot, and Dowling PID. Once the values for each method were found, the integral squared error method was used. This method represents the deviation from the final steady state value in the process, and in this case, Ziegler-Nichols method was chosen due to a smaller ISE value, but by a small amount compared to the Dowling synthesis method. Unfortunately, using a feedback controller only to regulate the reactor temperature by manipulating the fuel valve proved to be unsafe as O2 levels dropped below 9%. Additionally, our profit using this method was $20,425. Now, because only controlling the reactor temperature failed, we now implemented a feedback controller system regulating the furnace temperature by manipulating the fuel flow valve. As we can see, we followed the same strategy as with our first process identification test, where we made a 10% step change input at around 300 minutes into the test. In this case, our initial steady state value was 1,220 degrees Fahrenheit, and our final steady state value was 1,243.5 degrees Fahrenheit. Once we found this, we were able to once again find the gain of the system, the time constant, and the delay, which were then put into a transfer function for the process. Once these values were found, we once again tested the three tuning methods and found out that the Dowling synthesis method was better due to the lower ISE value. The values seen in the table here were the ones used for the feedback controller for the furnace temperature. Once these two controllers were implemented, we could see an increase in profit, which now was $21,096. However, there was still a concern in safety because the O2 levels would still drop below 9%, which meant that we would have to navigate some other options and schemes for the process. After our initial feedback controller implementations, we realized that ratio controls would have to be combined with another type of controllers to regulate the excess O2 level so that safety requirements would be met. In this case, the reactor temperature had to be regulated to maintain normal conditions of 800 degrees Fahrenheit, and the furnace temperatures had to be regulated to maintain a normal condition of 1,200 degrees Fahrenheit. For this, a feedback controller was implemented on the reactor temperature rather than the furnace temperature, because when the feedback temperature controller was implemented on the furnace temperature, the reactor temperature deviated too much from the set point. In this case, due to safety reasons, we had to cut profit. As we can see here, after implementing the feedback and ratio controllers, the reactor and furnace temperatures would be controlled as we wanted, and the oxygen would stay above 9%, although it would oscillate widely. To try to maximize profit, in addition to the feedback and ratio controllers, a feed-forward controller was implemented to try to regulate the ambient temperature, which is considered a disturbance variable. This combination then was tested to see if the data profit would increase and if the disturbance variable would also be regulated. With these three controllers acting at the same time, the temperatures of the furnace and the reactor were controlled even better, and the oxygen levels stayed above 9%, but it would still oscillate widely. Here, my groupmate Andrew Chadwell will present the Simulink demo and a conclusion regarding our final control scheme.
We apply a robust control strategy involving a double cascade loop combined with a ratio controller to enhance the efficiency and safety of the process. On the left, we have the Simulink model, and on the right is the PDF diagram. The first inner loop links the fuel flow rate to the fuel valve, resulting in the fastest response among the controllers. The second inner loop ties the furnace temperature to the fuel flow rate, showing a slower response. The outer loop connects the reactor temperature to the furnace temperature with the slowest response. We use the Dahlin PI method to adjust the inner controllers, while a PID was used for the outer controller. Increasing the flow valve to 60% open led to a boost in daily profit, and the ratio controller set to 110 ensures safe operations without excess oxygen dropping below 6%. Additionally, we have a proportional controller on the excess oxygen levels, controlling close to normal operating levels without dropping below 9%. We are going to run our simulation in Simulink developed by MATLAB. In the double cascade controller, three key controllers work together to regulate the naphtha cracking process. The inner one PI controller relates the fuel valve to the fuel flow rate. The inner two PI controller relates the fuel flow rate to the furnace temperature. The outer PID controller relates the furnace temperature to the reactor temperature. The set point for the fuel valve is set at 60% open, a decision aimed at maximizing daily profit. Additionally, a ratio controller plays a crucial role by linking the airflow rate to the fuel flow rate. This ensures the process operates safely, maintaining excess oxygen levels above 9%. Here are the key outcomes. Furnace temperature stays around the normal operating temperature of 1200 degrees Fahrenheit. Reactor temperature stays around the normal operating temperature of 800 degrees Fahrenheit. And excess oxygen levels remain above 9%. This integrated control strategy not only optimizes profit, but also ensures the safety and stability of the entire naphtha cracking process. The double cascade control demonstrates resilience against unmeasurable disturbances, including fuel composition variations, fuel supply pressure, and temperature fluctuations. In conclusion, our simulation indicated that the double cascade with ratio control not only optimizes profit but also ensures safety and robustness against unmeasurable disturbances.
As we can see here, controlling the excess oxygen near normal operating conditions with the PID controller increased the profit. The cascade controller could account for unmeasurable disturbances on the fuel composition variations, fuel supply pressure fluctuation, and temperature fluctuations. We concluded that the double cascade controller option was a better choice compared to the other options previously mentioned. Finally, as we can see here, we compared the profits of the three combinations that we explored. For the feedback and ratio combination, we got $20,512. For the feedback, ratio, and feed-forward combination, we got $21,163. And for the double cascade and ratio combination, we got $25,052. As we can see, the most profitable combination was the double cascade and the ratio, and it was also the one that met the safety requirements that we set at the beginning. Thank you so much for watching our presentation.